Hey everyone, welcome to Simplilearn's YouTube channel. In today's live session, we will talk about the most important topic of software development, which is none other than dynamic programming. But before we begin, let me tell you guys that we have daily updates on multiple technologies. If you're a tech geek in a continuous hunt for latest technological trends, then consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now, without further ado, let's get started with the agenda for today's discussion. First, we will start off by understanding what is dynamic programming and its fundamentals. Then, we will dive deep into the various problem statements based on dynamic programming, starting with the longest common subsequence, then longest increasing subsequence, later the subset sum problem, followed by that we have the longest common substring. Next, we will learn the matrix chain multiplication. Moving ahead, we will learn minimum edit distance. Now we will get into some popular dynamic programming problems, which are the Knapsack problem, the coin change problem, Floyd-Warshall algorithm, Bellman-Ford algorithm, and finally we will conclude by discussing the Tower of Hanoi. I hope I made myself clear with the agenda, so let's get started. Over to our training experts.
Meet Rachel. She enjoys tackling puzzles because they allow her to develop new emerging skills in a fun way. That is why she buys puzzle books from time to time. One day, while reading through one of her puzzle books, she came across a two-player tic-tac-toe game. She discovered one weird fact while reading the rules of this tic-tac-toe game. There are 2,55,168 ways to make a single move in this puzzle game. This fact captivated her interest, encouraging her to begin playing this tic-tac-toe puzzle game. Rachel began playing this game with her friend Alex, who already knew how to play this game. As a result of her repeated failures, Rachel became frustrated and started to question how she could go on a winning streak. After a few games, Rachel started remembering the outcomes of each of her moves, which contributed to her failure in previous games. By using those memories of her previous games, she started getting hold of the logic behind object placement in tic-tac-toe puzzle. Rachel's ability to memorize things helped her decide where to place an object on the tic-tac-toe board. As a result of her hard work and commitment to learn from her experiences, she went on a winning streak against Alex. To solve complicated permutation issues, the dynamic programming paradigm employs a similar concept of memorization. Furthermore, this dynamic programming paradigm is completely based on the philosophical idea that people who do not remember the past are condemned to repeat it. The dynamic programming principle states that if we can solve smaller subproblems, then their learnings can be memorized to solve the larger problems. This fundamental notion is acknowledged as a foundation of dynamic programming. Moving ahead, let's look at the broader picture of what is dynamic programming. Dynamic programming is defined as algorithmic paradigm that solves a given complex problem by breaking it into several subproblems and storing the result of those subproblems to avoid the computation of same subproblem over and over again. The divide and conquer strategy is quite similar to the dynamic programming approach. We solve problems in each of these paradigms by combining the solutions of smaller subproblems. However, in divide and conquer, the subproblems do not repeat themselves, whereas in dynamic programming, the condition is entirely opposite. Well, that means dynamic programming has different properties than the divide and conquer approach, and the problems which abide by those properties can only be solved using dynamic programming technique. So moving forward, let's discover the properties of dynamic programming. The first property that we have is optimal substructure. If we can establish a recurrence relation for a given problem, then it is said to have an optimal substructure. To understand this property, let's have a look at an example. The example that we are going to discuss is called the coin change problem, which is one of the most famous DP problems. In this problem, we have to construct a coin combination with the least potential number of coins, resulting in the desired final amount. Let's say we have a limitless supply of $50, $20, $10, and $5 coins, and the amount for which we need the least possible number of coins is $85. So, To formulate the solution, we'll have to traverse through all possible permutations of coins. The most logical solution to this problem is to add the coin of largest value at each iteration, which does not take us past the expected amount, that is $85. That means we break this problem into several iterations by choosing the coin of highest value at each iteration. This conversion of larger problem into smaller subproblems is known as optimal substructure. The next problem we have is an overlapping subproblem. If the subproblems recur while implementing a solution to the broader problem, then that problem is said to have an overlapping subproblems. Formulating recurring relation is the sole technique to determine if a given problem has an optimal subproblem or not. To understand this better, we'll have a look at an example of a Fibonacci series program. But before we get into details of that, we would like to ask you what dynamic programming or competitive programming topic would you like us to address next. You can mention the topics which you have doubts about in the comment section below, and we'll surely create an exciting video about it in the next few days. So guys, make sure you post a comment with the DP or competitive programming topics you'd like us to cover in upcoming videos. Now coming back to dynamic programming, we'll cover the mathematical interpretation of Fibonacci series program.
If getting your learning started is half the battle, what if you could do that for free? Visit Skill Up by Simplilearn. Click on the link in the description to know more.
The Fibonacci sequence is a group of numbers that frequently appears in nature. Each number in this series is the sum of two previous numbers that come before it. The sequence goes like 0, 1, 1, 2, 3, 5, 8, 13 and so on. Let's say the n is iterator element to calculate consecutive Fibonacci numbers. And for the first two iterations, that are 0 and 1, the resultant Fibonacci values will be simultaneously 0 and 1. Otherwise, the Fibonacci values will be the sum of previous two Fibonacci numbers in the sequence. That means when the value of an iterator element becomes 2, the consecutive Fibonacci number for it will be the sum of previous two numbers in the sequence, that is 0 and 1. So the resulting Fibonacci number will be 1. Now, when the iterator element n becomes equal to 3, the consecutive Fibonacci numbers for it will become 2. For the next iteration, n is equal to 4. The Fibonacci values will be the sum of 1 and 2, that is 3. When n becomes equal to 5, the resultant Fibonacci numbers will be 5. And similarly, the further numbers in sequence can be calculated. And now, if you observe the Fibonacci problem closely, you'll see that the breakdown of bigger problem is done into smaller subproblems in previous slide. This means the Fibonacci sequence problem has an optimal substructure, and the program for the Fibonacci sequence also represents the same. These highlighted statements are representing the recurrence relation in our Fibonacci program. Now what about the overlapping subproblems? Well, a problem is said to have an overlapping subproblems if any subproblem repeats while implementing the solution to the broader or larger problem. Let's say we want to calculate a Fibonacci number for n is equal to 5. The first activation record that will enter the memory stack will be fib of 5. And to calculate the Fibonacci value for number 5, our recursive program will call function fib4 and fib3. Further, to calculate fib4, the IDE will invoke fib3 and fib2. Next, it will calculate the sum of fib2 and fib1 to calculate the value of fib3. And further, it will invoke fib1 and fib0 to contemplate the value of fib2. Now we have generated the right side of our call stack tree hierarchy. Similarly, the other missing pieces will get calculated by the compiler with the help of recursive calls. Now, if you observe this activation hierarchy, you'll get that few subproblems are repeated in this problem. The fib3 has been calculated twice, and the fib2 has been calculated 3 times in our program. This repetition of the same subproblem while solving more significant problem is called as overlapping subproblem property. Due to the multiple calls, the computational complexity of recursive programs almost increases exponentially, and those calculations are entirely unnecessary. But before we understand how to avoid all unnecessary computation, let's try to figure out the time complexity of our fifth function. Look at the time complexity relation written over here. This says that the time taken to calculate fib n will be equal to the time taken to calculate fib of n minus 1 plus time taken to calculate fib of n minus 2 plus the time taken to add these numbers together. Clearly, for n is less than or equal to 1, the fib of n is going to be big of 1 as we are not going to make any recursive calls for them. Also, intuitively, we can say that t of n will take big O of 2 to the power n. We can contemplate this from the recursion tree drawn on the left side. For n is equal to 5, we get a binary tree of depth 5. For n is equal to 4, we get the binary tree of depth 4 and so on. This implies that the time complexity of our algorithm grows at an exponential rate, and graph shown on your screens depicts that. Moving ahead, we'll try to understand how we can reduce this computational complexity using dynamic programming. The computational complexity can be removed by memorizing the result of subproblems. In terms of computer science, we can refrain from doing unnecessary computations by utilizing the memory to store the results of subproblems. In dynamic programming, we calculate the result for subproblems and store it in memory allocated by an operating system. When that same subproblems get activated in our call stack, we access the memory in order to return the result that we have calculated previously. Now you must be thinking about how we can store the result in memory. Well, we can store the results in two ways. The first one is memorization and the second one is tabulation. In the case of memorization, we store the result in memory whenever we solve a particular subproblem for the first time. Whereas in the case of tabulation, we per-compute the solution in a linear fashion and store them in a tabular format. Memorization is also known as top-down approach, whereas tabulation is known as the bottom-up approach. In general, these names are assigned to these methods based on how they approach problem solving. The first one saves result in memory based on call stack occurrences. The second one, on other hand, solves the subproblem in sequential manner. For the top-down approach, we maintain a lookup table. When we compute any subproblem, we store results in lookup table. And when the recurrence of this subproblem happens, we directly fetch its value from our lookup table. Whereas in the case of bottom-down approach, the solution is built from the bottommost case. In addition, the memorization process is recursive. However, the tabulation process becomes iterative. If we implement the Fibonacci series program using top-down approach, then the code for function fib will look something like this. And this one additional step, fib n is equal to res, will do the memorization job for us. If we develop a Fibonacci sequence program using bottom-up approach, our program will look something like this. This highlighted for loop part calculates solution to all subproblems from the base case. I hope you guys are clear with both methods of dynamic programming. Now moving ahead, we'll discuss when to implement dynamic programming solution for any given problem. Remember guys, you can solve any problem using dynamic programming which abides by the properties of dynamic programming. Most frequently, you will come across the minimization and maximization problems which are readily recursive in nature. If you need exhaustive solution for these problems, then you can solve them using the dynamic programming paradigm. The permutation combination problems can also be solved using dynamic programming. The problem statement beginning with find the number of weights are the famous permutation problems that can be solved using dynamic programming approach. The term longest common subsequence clearly directs us towards some sort of relation between two sequences. A sequence is nothing but a series of elements that occurs in same order but are not necessarily contiguous. From this definition, we can say that the longest common subsequence will be the term that both given strings will contain. To understand it more clearly, let's have a look at an example. In this example, I have taken two strings. There is nothing like substring here, right? If you have studied the KMP algorithm, you'll remember the problem as string and substring. In that problem, we had to find the substring inside a given string. But this scenario is totally different from that. We'll be dealing with two different strings here. Here, you can clearly see that string 1 is larger and string 2 is relatively smaller. Now, for these two strings, possible common subsequences are as shown on the screen. And from this, you can clearly say that the longest common subsequence will be CDE. Moving forward, let's dive further into this LCS problem to understand the logic behind it. The problem statement for the LCS states that given two strings, find the length of common subsequences present in both the strings. That means in this problem, we'll be given two different strings with length m and n respectively. And from these two strings, we'll have to find the longest common subsequence with length k. Let's consider these two strings present on our screens. We'll try to find out the LCS for both of these strings here. We'll try to map patterns present in string 2 to string 1. Now let's pick the first character in string 2, that is Z. Now we will match this character to the character present in string 1, and the first character is X. So we'll map it with X, but Z and X do not match. Hence, we'll move towards the next character. Next character is Y, and Z and Y also does not match. Hence, we'll move to the third character, that is Z. Here, we have found the match. So what we'll do is we'll include Z into our longest common subsequence. The next character in our sequence is A, and we have A in string 1 as well. Hence, we'll include A in our longest common subsequence. The next character in string 2 is D, and we have found match for D in string 1 as well. Hence, we'll include it in our longest common subsequence. The final character in string 2 is F, and we have found F in string 1 as well. Hence, we'll also include it in our longest common subsequence. Finally, the longest common subsequence for string 1 and string 2 will be ZADF. Moving forward, let's discuss one more problem to understand LCS clearly. Here you can see that Z is present in both the strings. Thus, we'll include it in our LCS string. The next character is Y. It is also present in string 1, but the rule of LCS says that the sequence of character should not be changed, and here the mapping line of Z and Y are intersecting. So we'll discard character Y here, and we'll pick the next character in string 2. That character is D. And D is not intersecting with any other character, hence we'll add it to our LCS string. Now, the next character B is also there in string 1, but we cannot insert it in our LCS string as it intersects with the mapping line of character D. Thus, we'll discard this character. The next character F can be added to our LCS string as it does not intersect with any other mapping line. So, the first LCS sequence will be ZDF. And due to multiple intersections, there is possibility of having another sequence that can be larger in length than the previous sequence. For this sequence, we'll begin from the second character of string 2, that is Y. And Y is present in string 1. Thus, we can add it to the LCS. Next, we can add D to our LCS sequence. After this, we have B, but B cannot be inserted into LCS as it is intersecting with D. Hence, we'll discard it. And finally, we'll include F into our LCS sequence. In this problem, both the sequences have the same length. Hence, both of these sequences will be considered as longest common subsequences. I hope that you guys have understood the logic behind finding the longest common subsequence, cause we have a challenge for you guys to assess your understanding of the LCS. For these given sequences, you are supposed to find out the longest common subsequence. The options for this problem are BABC, BACE, and BCE. You all can drop your answers in the comment box below. Let's see how many of us can get this right. Now moving forward, we'll build a solution for LCS using recursion. So let's visit the code editor and develop the C program for longest common subsequence. The two strings for which we are going to find LCS are xy and xpyq. Let's create a function to get started with LCS implementation. I'm going to name this function as int LCS, and inside this function we'll pass the references of two character arrays. The first will be char star a comma char star b. The next arguments will be the lengths of these character arrays, int x and int y. Now we'll move to the function body of LCS. The first condition we'll evaluate is if the character array are empty or not. Because if character arrays are empty, then definitely there won't be any sequence to find out. So when we reach x equal to 0 and y is equal to 0, we'll return 0. For that, we'll write a condition if x equal to 0 or y equal to 0, then return 0. Now, the next condition, when both x and y won't be 0, we'll check if the last character of both character arrays match or not. For that, we'll write another if condition. If a x minus 1 equal to b x minus 1, then we will return 1 plus LCS a comma b comma x minus 1 comma y minus 1. Once this condition gets fulfilled, we'll return 1 plus recursive call to LCS function with inputs decrease in size by 1, that is x minus 1 and y minus 1. Now, if both the previous conditions fail, then what we'll do is we'll go into this else part, and inside this else part, we will return max of LCS a comma b comma x comma y minus 1 or LCS a comma b comma x minus 1 comma y. We are missing semicolon here. Okay, and dot here. So we'll change it. Now, this statement will get executed when there is no character match. If characters don't match, we'll move either way, one character in first string A or one character in second string B, and check whichever gives maximum, and we'll take that into consideration. Most of the time, this condition will get satisfied. To find out the maximum, we'll have to create a manual maximum function. So for that, we'll create a new function, that is int max, and we'll pass arguments int m comma int n. Now inside this function, we'll write a ternary condition, that is return m greater than n question mark m colon n semicolon. So this will return the maximum value between m or n. With this, we have successfully completed the LCS function. So moving forward, let's work on our driver function. In driver function, what we'll do is we'll create two character arrays at first. So for that, let's enter into this main function and we'll create character array A, and inside A we'll pass x and y. inside character array B will pass X, P, Y, Q. Okay. And will store the lengths of these character arrays into X and Y. For int X is equal to strlen A, and for int Y strlen B. We'll add semicolons here. And finally, we'll make call to our LCS function using the printf statement. The printf statement that will write is length of LCS is modulus D, comma LCS A, comma B, comma X, comma Y, semicolon. And finally, we'll add return 0. I hope our code is bug free now. So let's run it and check if it is bug free. That's fine. Here we are getting error, but it is not exactly an error. We have implicitly declared function max here. So that's why we are getting this flag problem, but we are actually getting output as well. So the output that we are getting is 2 here. And if you check both the strings, then you can find out that character array A is implemented inside character array B, and the length of common sequence is 2 here. So with this, we can say that our recursive implementation of LCS is successful. Now moving forward, we'll visit PowerPoint to understand why recursion is not an ideal approach to solve this problem. To understand the complexities associated with longest common subsequence problem implementation using recursion, we'll formulate a recursive tree by going through the steps of a program that we have created previously. So let's do that here. As you can see in this LCS function, the first step we perform is checking if both the strings are empty. If they are not empty, then we check if the last character of both strings matches or not. Thus, the first call to the LCS function will check for the match of last two characters. If characters don't match, which is true in this scenario, we move either one character in string A or in second string B, and we'll choose whichever produces maximum value. So, if we reduce B by 1 and keep the A same, then we have a character Y in both the strings. Whereas, if we keep B the same and reduce A by 1, then we have X and Q, which don't match with each other. First, we'll evaluate the left side of our recursion tree. And here, we have a character match. Thus, we'll enter if condition where characters do match, that is this condition. And it says that return 1 plus both the character arrays with size reduced by 1. And by doing that, we get two different characters X and P here. Now, as these characters do not match, we'll move position by 1 in both the strings. By doing that, we get these results. And here, if you observe, the left child has a character match. Thus, we'll add 1 and reduce the size of both character arrays by 1. And with this step, we reach the end of our strings. Now let's work on the right side of our recursion tree. In this case, we have distinct characters. Thus, we'll move by 1 in both the character arrays, and the resultant child nodes don't have characters that match. Furthermore, the right child reaches the null index. Hence, now we will just expand the left child. In addition to that, we can move positions only in character array B as we have reached the end of character array A. For this move, we do not have any match, so we'll reduce the position of B by 1 again. And here we get a match and also reach the end of both character arrays. Now, the next step will be for evaluating LCS length by backtracking our recursive tree. First, we'll consider the left side. So let's begin from the bottom of left side. At the bottommost child, we have some value equal to 0. For the next step, we'll have some value 1, as we will add 1 here. For the next step as well, we'll have to add 1 to our sum value. Thus, the sum value will become 2 here. And the overall sum for the left side of recursive tree will result into 2. Whereas for right side, the sum will become 1, as there is only one match. Now, the side which has maximum sum value will be returned as a result of this LCS program, which will be 2 in this case. The complexity for this recursive LCS program will be 2 to the power n. Now, for these two strings which have small length, you can see that the complexity will be equal to 2 to the power n, where n belongs to the depth of binary tree. That is huge complexity. If you look at the complexity graph, you'll get parabolic graph, which will increase continuously or exponentially. However, this problem can be resolved by using dynamic programming paradigm. Moving further, we'll try to analyze how dynamic programming can reduce the computational complexity of LCS problem. Here, we'll try to solve LCS problem using the tabulation method in order to understand how tabulation can reduce space complexity by making fewer computations. The LCS function for tabulation will be iterative. Hence, we'll understand the computation with the help of tabular representation. The columns will represent character array B and rows will represent character array A. Furthermore, we have added the null values to the table. Hence, initially we'll set the field values for null row and columns as 0. Now here, we'll move through the row of character X. For the first iteration, we hit the match. Hence, we'll add 1 to the diagonal element. So, 0 plus 1 will become 1. For the next iteration, we get X and P, which do not match. Hence, we'll continue with 1. Next, we have X and Y, which also do not match. Hence, we'll continue with 1. Remember guys, the highest value between these two fields will be picked every time. For the next move, the value 1 will continue. Now moving forward, we'll move towards the Y row. Here, for both X and P, the values will remain 1 as we don't have the character match. But for the next field, we'll have a match. Hence, we'll add 1 to the diagonal field. The value for this particular field will become 2 now. For the last field, the value 2 will get continued as it is the highest field than another comparative field. And you can see that we have found the accurate result here, which is 2. I hope this tabulation logic is clear to all of you, cause moving forward, we'll develop a C program for the same. Now, in order to get started with this tabulation function, we have created int LCS function with few arguments. These arguments are similar to the recursion. In this tabulation LCS function, we'll first create the 2D matrix for performing the computation. The statement that will help to do that is int L x plus 1 and y plus 1. So this will create a 2D matrix of size x and y. We'll also initialize few variables for using them inside looping process. So I'll create two variables, int I and j. Next, we'll create a nested loops for traversing through both arrays at the same time and updating the computational table. For that, we'll create for loop, and inside this for loop, we'll begin from I is equal to 0 to I is greater than equal to x, and we'll increment the I. And inside this for, we'll create another for loop, and we'll begin this with j is equal to 0 to j less than or equal to y, and j plus plus. After that, we'll write the first condition to set null values for the null row and column fields. So the statement that we'll write is if I is equal to 0 or j is equal to 0, then set L I j equal to 0. If this condition fails, then we'll check if the last character match with one another. If they match, then we will return 1 plus both array fields reduced by position 1. For that, we'll write condition else if a I minus 1 equal to b j minus 1, and instead this else if condition, we will set L I j is equal to L I minus 1 j minus 1 plus 1. And if this condition fails, then we'll enter into else loop and we'll pick Lij as maximum of L I minus large L, and here as well it should be large L I minus 1 j comma L I j minus 1. And we'll get out of these for loops and we'll return the output, that is L X and Y. I hope this should be fine now. So let's run our code and check if there is something wrong. We'll save this as LCS underscore DP. Okay, so we are getting 3 problems here. Okay, so I have inserted O here instead of 0. And there is one more mistake. So I have called function max as max here and have named it as maximum here. So we'll have to change this to maximum. I think this should be fine now. So let's run our code again. Okay, we'll have to save this. So we'll paste Control S and we'll rerun it. Yeah, so we are getting our output here. The length of longest common subsequence is 2. So if you observe here, the output that we have got using dynamic programming is in 5.58 seconds. And the time that was taken for LCS recursion was around 8 seconds. So you can see that the complexity has been reduced, the time complexity and space complexity as well. So that is why the dynamic programming is better approach than recursive programming paradigm. I hope the longest common subsequence problem implementation using dynamic programming is clear to all of you out there.
In this problem, we have to find the length of the longest subsequence of a given sequence such that all elements of the subsequence are sorted in the increasing order. For example, as you can see in the picture, the length of the longest increasing subsequence for the set is 5 and the longest increasing subsequence is 10, 12, 30, 35 and 60. Now, let's discuss the algorithmic solution to the longest increasing subsequence. First, we will create another array of the same size as the original array with element as 1. Then, we will discuss the nested loop and compare the value of array elements. If value comes out to be increasing order, then we will increment the corresponding new array element's value. Now, we will repeat this for the every possible set until every set is exhausted. Now, the maximum element in the new array will be considered as the length of the our longest increasing subsequence. We have now discussed the problem statement and the algorithmic solution to the longest increasing subsequence problem. Now, let's implement this solution in the code editor. We will start with a function that will return the length of the longest increasing subsequence in the array arr of size n. So int lis, its argument will be int array arr, comma int n. We will declare int less n. Now less at 0 will be equals to 1. Now we will compute the optimized list values in the bottom-up manner. So for int I is equals to 0, I less than n, I plus plus. Now we will give less at every ith position is equals to 1. Now we will insert another for loop inside as a nested manner. So for loop int I j is equals to 0, j less than I, j plus plus. Now if arr at I is greater than arr at j, and less at I is less than less at j plus 1, then we will update list value at I is equals to list value at j plus 1. After that, we will return the maximum value of list. So return star max underscore elements less comma less plus 1 plus n. Now we will write the main block. We will declare int the array its elements as 10, 7, 12, 30, 22, 35, 60, 9. Then we will find the size of this array. So int n is equals to size of arr divided by size of at arr at 0th location. Now we will print cout length of list is handle cout list arr comma n. Let's execute this. As you can see, we are getting the length as 5, just like we have discussed during the algorithmic solution. Let's get started with the problem statement. We will be given a set of non-negative integers and a value of variable sum, and we must determine if there is a subset of given set with a sum equal to a given sum. Now, let's discuss the algorithmic solution to the subset sum problem. First, we will create a 2D array of size arr size plus 1 multiplied by target plus 1 for the type boolean. Next, the state dp I, j will be true if there exists a subset of elements from a from 0 to I with a sum value equals to j. Let's look at the pseudocode. Here, if the current element has a value greater than the current sum value, we will copy the answer for previous cases. And suppose the current sum value is greater than the ith element, in that case, we will see if any of the previous states have already experienced the sum equals to j, or any previous states experience the value j minus a at the I value, which solves our purpose. We have now discussed problem statement and algorithmic solution to subset sum problem. Now let's implement this solution in the code editor. We will start with the Boolean function isSubsetSum, which will return true if there is a subset of set with the sum equal to the given sum. So bool is subset sum int arr comma int n comma int sum. Now the value of the subset ij will be true if there is a subset of set from 0 to j minus 1 with sum equal to I. So bool subset n plus 1 to sum plus 1. Now if sum is equals to 0, then the answer will be true. So for int I equals to 0, I less than equals to n, I plus plus subset at I comma 0 is equals to true. Now if sum is not 0 and set is empty, then we will answer false. So for int I equals to 1, I less than equals to sum I plus plus. Now in this case, we will check at subset 0, comma 1, comma I equals to false. Now we will fill the subset table in bottom-up manner. So for int I equals to 1, I less than equals to n and I plus plus, we will add another for loop. Int j is equals to 1, j less than equals to sum j plus plus. Now if j is less than arr I minus 1, then subset I comma j will be equals to subset I minus 1 and j. Now if j is greater than equals to arr at I minus 1, then subset at I comma j will be equals to subset I minus 1 to j, or subset I minus 1 to j minus arr I minus 1. Now we will return subset at n comma sum. Now let's write the main block. So we will create int set, which will be equals to values like 3 comma 34 comma 4 comma 12 comma 5 comma 2 and so on, and we will have to find a subset with the sum equals to 9. Now let's find the size of this set. So int n equals to size of set divided by size of set at 0th position. Now if is subset sum with with arguments as set comma n comma sum is equals to true, then cout found a subset with given sum. Else cout no subset with given sum is found. Basically, if this is subset sum gives true, then we will print the found a subset with given sum. Otherwise, we will print no subset with given sum is found. Now let's try to execute this. As you can see, we are getting found a subset with given sum, which means we have found a set with the sum as 9, which is 4, 5. Let's get started with the problem statement. The longest common substring problem involves finding the length of the longest string, that is, the substring of two or more strings. There might be a number of solutions to a situation. Now, let's discuss the algorithmic solution to find the longest common substring. First, we must determine the length of the longest common suffix for each substring of both strings and save it in the database. Now, If the last characters in the longest common suffix match, their length will be reduced by 1. Or if the last characters in the longest common suffix do not match, then the result will be 0. Now we will look at the suffix of distinct substrings that ends at different indices. Finally, we will conclude that longest common substring is the longest common suffix with the maximum length. We have now discussed the problem statement and the algorithmic solution to find the longest common substring. Now, let's implement this solution in the code editor. We will start with a function that will return the length of the longest common substring of a string x and y. Int lc sub str its argument as star char x, comma character pointer y, comma int the size of the first string x, comma int n. This will be the size of the another string y. Now we will create a table to store the lengths of longest common suffixes of string. Now we will create a array lcsuf to store the length of the longest common suffix. So int lcsuf at m plus 1 and n plus 1. And another variable result equals to 0. This will be used to store the length of the longest common substring. Now we will follow the steps to build the lc suffix in the bottom-up fashion. So for int I equals to 0, I less than equals to m, I plus plus. Another nested loop for int j is equals to 0, j less than equals to and j plus plus. Now the first row and the first column entries will have no logical meaning. They will be used only for the simplicity of the program. So if I is equals to 0 or j is equals to 0, then lcsuf at I comma j will be equals to 0. Else if x at I minus 1 is equals to y at j minus 1, then LCS at I, j will be equals to LCS at I minus 1 and j minus 1 plus 1, and the result will be equals to the maximum of result, comma LCS at I, j. Else LCS at I, j will be equals to 0, and we will return result. Now let's write the main block. So we will have string char x is equals to calm down, and another string char y is equals to keep calm. Now we will store the length in m equals to strlen of x and int n will have strlen of y. Now we will print the length of longest common substring. LCS sub str at x, y, m, n. Now let's try and execute this. As you can see, we are getting the length of the longest common substring as 4, which was calm.
Let's get started with the problem statement. We will be given a sequence of matrices. We have to find the most efficient way to multiply these matrices together. The problem is not actually to perform the multiplication, but merely to decide in which order to perform the multiplication to get the minimum operations on a multiplication. Now, let's discuss the algorithmic solution to the matrix chain multiplication. First, we will take matrix sequence and divide it into two subsequences. Then we will calculate the minimum cost of multiplying out each subsequence. Then we will add these costs together and in the price of multiplication the two result matrices. Finally, we will repeat these steps for every possible sequence of matrices that can be split and take a minimum over all of them. We have now discussed the problem statement and the algorithmic solution to matrix chain multiplication. Now, let's implement this solution in the code editor. First, we will define max10. So, hashtag define max10. Now, we will look up tables to store the solution to already computed subproblems. So, int lookup with dimension as max. Now we will write a function to find the most efficient way to multiply a given sequence of matrices. Int mcm int dems comma int I comma int j. Now we will write our base case, that is one matrix. So if j is less than equals to I plus 1, then we will return 0. Now what if it stores the minimum number of scalar multiplication, that is cost, needed to compute matrix mi plus 1 to mj, which is equals to mi to j. So int min should be equals to int underscore max. Now if the subproblem is seen for the first time, then we will solve it and store its result in the lookup table. So if lookup at I comma j is equals to 0, then we will take the minimum over each possible position at which the sequence of matrices can be split. So for int k is equals to I plus 1, k less than equals to j minus 1, and k plus plus. Now we will recur for m from I plus 1 to mk to get an ixk matrix. Int cost will be equals to mcm dems comma I comma k. Now we will recur for m k plus 1 to mj to get an kxj matrix. So cost plus equals to mcm dims comma k comma j. Then we will write the cost to multiply to ixk and kxj matrix. So cost plus equals to dims at I multiplied by dims k multiplied by dims at j. Now if cost is less than min, then min will be equals to cost. Now we will store min at lookup at I comma j. Now we will return the minimum cost to multiply mj plus 1 to mj. So we will return lookup at I comma j. Now let's define a matrix int dims equals to 10, 30, 5, 60. Now we will find the size of this dims array. So int n equals to size of dims divided by size of at dims 0. Now see out the minimum cost is MCM at dims 0, n minus 1. Now let's execute this. As you can see, we are getting the minimum cost as 10. So our function is working flawlessly.
What is minimum edit distance? So the answer for this question is the number of editing operations required to convert one string into another is defined as minimum edit distance between two strings. The number of editing operations required to achieve this shortest distance is called as minimum edit distance. The insert operation is used first in the minimum edit distance, followed by the remove operation, and finally the replace operation. Now, let us look into a small example to understand minimum edit distance in a much better way. Assume that we need to convert string 1, that is glass, into string 2, that is grass. To convert glass into grass, apply the replace operation to the character R in the string 2. In this example, we only need to use one operation, that is the replace operation, to convert the string 1 into string 2. Next, we will look into another important example to see how minimum edit distance works in practice. In this example, we must convert string 1, that is UVWXYZ, into string 2, that is UAWYX. So, first we will look into the first character of the string 1, that is U, and the first character of string 2, that is also U. No changes are required because U character in the string 1 is same as the U character in the string 2. Next, we will compare the second characters of string 1, that is V, with the string 2, that is A. We must use the replace operation because V character in string 1 is not same as A character in string 2. We are now comparing string 1's third character with string 2's third character, that is W, for the same. No changes are required because W character of string 1 is equal to the W character of string 2. Now, we will look into the next character of string 1, that is X, because X character in string 1 is unnecessary, so we will remove the X character using the remove operation. The next character in string 1 is Y. We will compare it to the next character of string 2, that is also Y. So, no practical changes are required here since both the characters are equal to each other. Finally, we have the comparison of Z character from string 1, and we will compare that to the last character of string 2, that happens to be X. Now we will have to use the replace operation because Z character of string 1 is not equal to the X character of string 2. Now, to convert string 1 into string 2, we require 3 operations, that is 2 replace operations and 1 delete operation. So the final topic in this session is minimum edit distance using dynamic programming. Using the same example as before, we will continue with the minimum edit distance using dynamic programming. So in this example, we have a string that is UVWXYZ on the row side and another string that is UAWYX on the column side. We will use dynamic programming to convert one string to another to find the minimum number of operations required to perform this conversion. So our first row contains the first string, that is UVWXYZ, and our first column contains the second string, that is UAWYX. We then have an extra column and row stating that string 1 will require 6 edits to convert string 2 and string 2 will need 5 operations to convert to string 1. Let's get started on filling out the rest of the matrix. So, since the first character of string 1 is U and second character of string 2 is also U, so converting the U will not require any operations. So we have 0. Now, string 1 has 2 characters of U and V and string 2's first character is U. So it will take only one operation to convert from this to that. Next, we have U, V and W in string 1 and U in another string. Converting them will require 2 operations. With U, V, W and X in string 1 and in string 2, it would take 3 operations to convert. If we have U, V, W, X and Y characters in string 1 and U characters in string 2, we will need to convert them using 4 operations. Next, we will have 6 characters U, V, W, X, Y and Z and U character in string 2. It will take 5 operations to convert them. Let's fill up the second row with U characters in string 1 and U and A in another string to convert U to U plus A in one operation. Next, we have U plus V in string 1 and U plus A in another string. So converting them will take one operation. Because we have U, V and W in string 1 and U and A in string 2, converting these characters would require two operations. Next we have U, V, W and X in row side and U and A on the column side. These will be requiring three operations to convert. Next we have U, V, W, X and Y in string 1 and we need to convert it to U and A character of string 2. This conversion will take four operations. And now we have all six characters in string 1, U, V, W, X, Y and Z, and we need to convert it to U and A character from string 2. This conversion will take 5 comparisons. If you found it challenging to compute the number of operations using this method, we devised a new formula that states that if the character of string 1 is the same as the character of string 2, we get the diagonal value as the number of operations. But if the characters of both strings differ, we have minimum of let top and diagonal values plus 1. So using this formula, we filled all the matrix values to convert string 1, that is U, V, W, X, Y, Z, to string 2, that is U, A, W, Y, X. So the last value of the matrix, which is our answer, both string 1 and string 2 require three operations to perform the conversion.
Let's get started with the topic, what is knapsack problem? The knapsack problem is used to explain both the problem and the solution. It derives its name from the fact that the limited number of things that may be carried in a fixed size knapsack. Given a set of items with varying weights and values, the goal is to pack as much as value as possible into the knapsack while staying within the weight limit. Now let's discuss 0-1 knapsack problem. First, we will be given weights and values of n items. In this case, 6 items on the left. We will put these items in a knapsack of capacity W, or in this case 10 kgs, to get the maximum total value in the knapsack. Then we will have to fill this knapsack, but we can't break the item, so we must either pick the entire item or not pick at all. Due to this, sometimes it may even lead to a knapsack with some spare space left with it. Now, let's try to implement this in the code editor. We will start with the utility function that will return the maximum of two integers. So int max a, comma, int b. We will return if a is greater than b, then a else b. We will now write a function to return the maximum value that can be put in a knapsack of capacity W. Int knapsack int capital W, comma, int WT for the weight, comma, int value, comma, int n. We will declare int I, comma, w. We will create a vector inside a vector k n plus 1, comma, vector int capital W plus 1. Now we will build a table k in bottom-up manner. So for I equals to 0, I less than equals to n, I plus plus, we will have another for loop inside it. For loop with small w equals to 0, this small w will be less than equals to capital W with small w plus plus. Now if I is equals to 0 or w is equals to 0, then we will have k at I comma w is equals to 0. Else if weight at I minus 1 is less than equals to w, then k at I comma w will be equals to max of value at I minus 1 plus k at I minus 1 comma w minus wt, where wt is at I minus 1 comma k at I minus 1 comma w. Else we will have k at I comma w is equals to k at I minus 1 comma w. Now we will return k at n comma w Now we will write the main block. We will start with int value array, which will have elements as 60, 100, 120, and weight will be equals to 10, 20, 30, and the maximum capacity, the capital W, will be equals to 50. Now let's find the size of the value array. So int n is equals to size of val divided by size of val at 0th location. Now we will print cout knapsack at capital W, WT, val, n, and return it as 0. Let's compile it. As you can see, we are getting the value as 220, which means we are getting it because we are taking the elements with weight equals to 20 and 30, which comes out to be as 50. Let's get back to our slides.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
We have now discussed 0-1 knapsack problem. Now, let's discuss the fractional knapsack problem. Similar to the 0-1 knapsack problem, we will be given the weights and the value of n items. In this case, 6 items on the left. We will also be getting a knapsack with capacity W, or in our case 10 kgs, to the right. Now we have to get the maximum total value in the knapsack. Then we will have to keep filling this knapsack, but unlike 0-1 knapsack, we can break an item to get a maximum value of knapsack. Here we will break this 3 kg item into a 2 kg and 1 kg item to fill the knapsack. Now let's try to implement this in the code editor. We will start with the structure for an item which stores weight and corresponding value of item. So struct item int value comma weight. We will write the constructor as item with the argument as int var comma int wt weight where this value will be equals to val and this weight will be equals to weight. Now we will write a comparison function to sort items according to value by weight ratio. So Boolean function CMP with argument as struct item A, comma struct item B. Now double R1 is equals to double A dot value divided by double A dot weight. Similarly, we will write it double R2, which will be equals to double B dot value divided by double B dot weight. Now we will return R1 greater than R2, which means it will return true if R1 is greater than R2. Now we will write the main function to solve the problem. So double F knapsack with argument as int capital W, comma struct item ARR, comma int n. We will first sort the item on the basis of ratio. So sort ARR, comma ARR plus n, comma CMP. Now int current weight is equals to 0 and double final value is equals to 0.0. This will be result value in knapsack. So for int I is equals to 0, where I is less than n and I plus plus, now if adding the item won't overflow, then we will add it completely. So if current weight plus AR, ARR at I dot weight is less than equals to capital W, then current weight plus equals to ARR dot weight and final value will be plus equals to ARR at I dot value. Now if we can't add a current item, then we will add fractional part of it. So else int remain is equals to W minus current weight, then final value will be plus equals to ARR at I dot val multiplied by double remain divided by double ARR dot weight. Now we will break. Then we will return final value. Now let's write our main block. We will start with defining int W equals to 50. This will be the weight of the knapsack and item ARR equals to element as 60, 10, 100, 20, 120, 30. We will find the size of n int n equals to size of ARR divided by size of ARR at 0th location.
Now we'll make the function call. So cout maximum value can obtain equals to f knapsack w comma arr comma n. Let's execute this. As you can see, we are getting the maximum value as 240. That means our function is working flawlessly.
The coin change problem is defined as the total number of ways you can change the given amount of money using the coins. And we are provided with different types of coins, or coins of varying denominations and a specific amount, that is W. Let's look into an example. The denominations of the coins are 1, 2 and 3, and 5 is the weight. So how can we achieve a weight 5 with 3 coins? There are a number of ways to do this. First, we will need 5 1 rupee coins. The second way to make 5 is to use 3 1 rupee coins and 1 2 rupee coin. The third way of doing it is using 2 1 rupee coins and 1 3 rupee coins. The fourth way is to use 1 2 rupee coin and 1 3 rupee coin. And the last way is using 1 2 rupee coin and 1 3 rupee coin. There is no other way to make the number 5 using 1, 2 and 3 rupee coins. So in total we have 5 ways to make weight equal to 5 using these coins. Now we will see how dynamic programming can be used to solve the coin change problem. Let us suppose we have a different demonstration of coin as 2, 3 and 5, and we have to make the total sum weight as 8 with the same condition that we can use an infinite number of coin supplies. We must generate a table in the coin change problem using dynamic programming because we will store the results and use them later. So in this table, the column side will have coin values of 2, 3 and 5, and the row will have to store the weight by dividing it into smaller weights, because in dynamic programming we will divide problems into sub-problems that are 0, 1, 2, 3, 4 until 8. Here are 3 simple steps of solving the coin change problem with dynamic programming. The first step is to exclude the coin, the second step is to include the coin, and the final step is to add the first and second steps. Let's start with the coin of demonstration 2, and the sum is 0. So there's only one way to go, because if we don't choose the coin value 2, we'll obviously make sum or weight as 0. And the same goes for coin 3 and 5. So we'll write 1, 1 and 1 below the sum of 0. Now that the sum is 1, we can make it 1 using a coin value of 2. The answer is no. We can't make it 1 using a coin value of 2. So we will fill 0 in here. Next, we must make the sum 2 using 2 rupee coin, and there is only one way to do so. Use 1 2 rupee coin. Next, we can make a sum of 3 using a coin of denomination 2. The answer is no. So we'll mark this entry as 0. We can now make a sum of 4 by using a coin with a value of 2 rupee coins in only one way. So we'll update 1 as the location changes. In the same way, we will update the entire row of coin denominations too. Now that we have a new coin with a denomination of 3, we will have one trick. If the coin value is greater than the sum, simply copy the first values above. For example, if the coin value is 3 and the sum is 1, we will simply copy the value which is above, which is 0. Again, the coin value is 3 and the sum is 0, which is less than the coin value, so we will simply copy the value above, which is 1. Next, we have sum of 3 and coin value of 3 that is not greater than 3. We will now proceed with those simple 3 steps. If we exclude coin value 3, we simply copy the value above, which is 0, and if we exclude coin value 3, we subtract that same row weight, that 3 with coin value that is also 3, which gives us 0. And what we have below weight 0 in the same row is 1. So we will add both values, that 0 and 1, which gives us 1. Next, for sum 4, we exclude coin value 3. We must simply copy the value which is above, which is 1. And by including 3, we must subtract the sum value, which is 4, from the coin value, which is 3, which gives on. And what we have below sum 1 in the same row is 0. So we add 0 and 1, which is 1. So in the same manner, we will fill out all the entries for sum 5, 6, 7 and 8 of 3 coin denominations. Now that we have coin value 5, we use the same trick. If coin value 5 is greater than the sum of 1, which is true, we simply copy the values which are lying above the row. So we have done for the first row, that is 0. So by excluding coin value 5, and we are left with 2 and 3, and what we have of coin 2 and 3 in the same row is 0 and 1, and the sum of 0 and 1, which gives 1. And by including coin value 5, we have to subtract sum to coin value 5, which gives 0, and what we have below, the sum of 0 of the same row, which is 1. So 1 plus 1 gives 2. So we update the same. The sum is now 6 and the coin value is also 5. So if we exclude coin, the value 5, we are left with 2 and 3. And what we have of coin 2 and 3 is the same row, is 1 and 2, and the sum of 1 and 2, which gives 3, and we include coin value 5. We have to subtract sum of 6 with coin value 5, which gives us 1, and what we have below, the sum 1 of the same row, which is 0. So sum of 3 plus 0 gives us 3. We will update the same. So in the same manner, we will fill out all the entries of sums of 7 and 8 of 5 coin denominations. So in the end, we got 3, which is our answer, indicating that we have a minimum of 3 ways to make the sum of 8 using denomination coin value, which is 2, 3 and 5. Now in this video, we will go over all the steps that we went to solving the coin change problem with dynamic programming. First, we had a 2D array named coin change, which has I as the number of rows and j as the number of columns. Now in this algorithm, we will have 2 for loops, one for I and another for checking the values of columns within I, that is row. So the first loop runs from 0 to the maximum length of the coin, which is the coin dot length, and the second loop runs for the first column to the weight. If coins of I are greater than j, we simply copy coin change of I of j is equal to the coin change if I minus 1 of j. Otherwise, we must apply the 3-step formula coin change of I of j is equal to coin change of I minus 1 of j plus coin change of I of j minus coin of I. Lastly, we will see the practical implementation. So on my screen, you can see a program example for coin change problem. First, we finished all the necessary header files, standard library strings, which all the strings are defined, and console input-output library. So first, we have a function called collect, which has an array called sum and 2 variables called m and n for number of coins and number of weight. So this is our first function. So m is number of coins and n is the weight. Then in this function, we declared 4 variables, 2 counter variables and in variable for including the coin value and x variable for excluding the coin value. Then we declared our 2D array, which is a coin change array in which we need n plus 1 rows because the coin change is built from the bottom up using base case 0. Next we have two for loops, one for row that will run until the coin length is reached and another for column that will run until the sum or weight is reached. In this for loop, we will first include the coin value j. We get the value after subtracting the j value from the coin value I. If the coin value I is greater than 0, we simply assign the coin change of I minus the coin change of the same column. If we exclude the coin value from this, we have the condition that if jth value is greater than 1, we assign coin change of I of j minus 1, otherwise we assign 0. Alternatively, simply return the coin change from n of m minus 1. Next we have the main function, in which we declare the array of coin values and assign the coin values of 2, 3 and 5. Then we have the same m variable in which we divide the coin, and then we have variable n in which we have sum as 8, and finally we print the total number of coin combinations that sums up. Now let's quickly execute this program and see the output. So there you go, the program got successfully executed and we have the output over here. And this example we considered is the same which one we have discussed before, and the final value is 3 that you can see over here. And you can see the answer as the total number of combinations of coins that sum up to value 8 is 3.
Let's get started with the topic, what is Floyd-Warshall algorithm? The Floyd-Warshall algorithm is for solving the all-pairs shortest path problem. The problem is to find the shortest distance between every pair of vertices in the given edge-weighted directed graph. Now, let's discuss the algorithmic solution to the all pairs shortest path problem. First, we will initialize the solution matrix the same as the input graph matrix. Then, the solution matrix is then updated by treating all vertices as intermediate vertices. Our main goal is to pick all vertices one by one and update all shortest paths that involves the picked vertex as intermediate vertex. We have now discussed the Floyd-Warshall algorithm and the algorithmic solution to all pairs shortest path problem. Now, let's implement this solution in the code editor.
Choose from over 300 in-demand skills and get access to 1,000 plus hours of video content for free. Visit SkillUp by Simplilearn. Click on the link in the description to know more.
We will start by defining vertices. We will have 4 vertices. So, #define INF, which will be equal to 9999. Now, let's write a function to print the solution matrix. So, void print solution with the argument as int, a two-dimensional array dist with its y as v. We will come back to its definition later on. Now, we will write a function to solve all pairs shortest path problem using Floyd-Warshall algorithm. So void Floyd-Warshall int graph. This will also be the 2D array which has y as v. Now we will define dist 2D array. It will be the output matrix that will finally have the shortest distances between every pair of vertices. So int dist, its x and y will be v, comma I, comma j, comma k. Now we will initialize the solution matrix same as input graph matrix, or we can say that the initial value of shortest distance are based on shortest paths considering no intermediate vertex. So for I is equal to 0, I less than capital V, I plus plus. Another nested loop for j is equals to 0, j less than V, j plus plus. So distance at I comma j will be equals to graph at I, j. Now we will add all vertices one by one to the set of intermediate vertices. So before start of an iteration, we will have the shortest distances between all pairs of vertices such that the shortest distance considering all the vertices is set from 0 to k minus 1 as intermediate vertices. And after the end of an iteration, vertex number k is added to the set of intermediate vertices and the set becomes from 0 to k. So for loop k is equals to 0, k less than v, k plus plus. Now we will pick all vertices as source by one. I is equals to 0, I less than v, I plus plus. Now we will pick all vertices as destination for the above picked source. So for j is equals to 0, j less than capital V, j plus plus. Now if vertex k is on the shortest path from I to j, then we will update the value of distance I, j. So if distance at I, j is greater than distance at I, k plus distance at k, j, and distance at k, j is not equals to INF, and distance at I, k is also not equals to INF. Then distance at I, j will be equals to distance at I, k plus distance at k, j. Now we will call the print solution function for test. Now let's write the utility function to print solution. So void print solution and test. We will start with cout. The following matrix will show the shortest distance between every pairs of vertices. For loop int I is equals to 0, I less than capital V, I plus plus. For loop int j is equals to 0, j less than v, j plus plus. If distance at I, j is equals to INF, then we will see out INF. Else, we will see out the distance at I, j. Now we will see out and L. This will change the row for the matrix. Now let's write the main block. So we will define the matrix as int graph v, v, which will be equals to 0, 5, INF, 10. Next row INF, 0, 3, INF. Next row INF, INF, 0, 1. Last row INF, 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 0. Now we will call the Floyd Warshall function. So Floyd Warshall for argument graph. Let's execute this. As you can see, we are getting an updated matrix which shows the shortest distance between every pair of vertices.
So, Bellman-Ford algorithm solves the single shortest path problem when the edge weight can be negative without a negative cycle. When some of the edges of the dedicated graph have negative weight, the algorithm works correctly. When some of the edges of the directed graph have negative weight, this algorithm works correctly. when there are no negative weight cycles, we can determine the shortest path between source and destination. The Bellman-Ford algorithm detects and reports the presence of negative edge weight cycles in a graph. Based on the principle of relaxation, more accurate values gradually recovered an approximation to the proper distance until finally reached the optimum solution. After understanding what exactly is Bellman-Ford algorithm, we will now look into some of the steps followed by the Bellman-Ford algorithm. But let us look at one scenario. Given a weighted directed graph G is equals to V, E, that is vertices and edges, and a weight function W, the Bellman-Ford algorithm returns a Boolean value indicating whether a negative weight cycle can be obtained from the source or not. If such a cycle exists, the algorithm computes the shortest paths and their weights. The algorithm returns true if a graph has no negative weight cycles that can be reached from the source. Let us start with the Bellman-Ford steps for the algorithm and see how it works. Set the distance values of nodes to infinity except the source node. In the first, we must repeat the relaxation step v minus 1 times, where v is the number of vertices. So, if we have an edge from u to v, where u is the source node and v is the destination node, then v will be updated with a new distance value if the distance of u plus the cost of the edge uv is less than the distance of v node. Otherwise, we will not update it and we will skip it. All vertices should be relaxed once more. We have a negative edge weight cycle if we find a new shortest distance value. Otherwise, we do not have a negative edge weight cycle and can return to the answer in the last step. We have heard that the Bellman-Ford algorithm is used to detect a negative edge weight cycle in the graph for a long time. Let us see how the Bellman-Ford algorithm detects a negative edge weight cycle in the graph. Let us assume that we have a graph with 3 vertices with initial value as infinity as the weight of the graph. Because this graph has 3 vertices, we will relax it v minus 1 times, that is 2 times. In the first time of relaxation, the weight from 0 to 1 is 2. So, the cost of 0 to 1 will be 0 plus 2, which is equal to 2. So, because 2 is less than infinity, we will replace infinity by 2. Now, from 1 to 2, the cost will be 2 plus 1, which is 3, which is less than infinity. So, that we will replace by infinity by 3. After that, we have got 2 to 0. The cost will be 3 plus minus 4, which is equals to minus 1. And as we know that minus 1 is less than 0, we will replace it too. In the second time of relaxation, the weight from 0 to 1 is 2. So the cost from 0 to 1 will be minus 1 plus 2, which is equals to 1, and 1 is less than 2. So we will replace 2 by 1. Now, from 0 to 1, we have the weight as 1. The cost will be 1 plus 1, which will be equals to 2, and we know that it is less than 3. So, we will replace 3 by 2. Finally, from 2 to 0, we have weight as minus 4. So, the cost will be 2 plus minus 4, which is equals to minus 2. And minus 2 is less than minus 1. So, we will replace minus 1 by minus 2. We have finished the first 2 times of relaxation. So, let us try the third time. In the third time of relaxation, we have the weight from 0 to 1 as 2, and the cost will be minus 2 plus 2, which is equals to 0, and 0 is less than 1. So, we will replace 1 by 0. So, after performing the third time, we have minimum distance as 0, which should not happen because we only had to relax it twice. We must relax twice, but after the third time, we should find the shortest path. But after the third time, we have the smallest cost as 0, which should not happen, indicating that there is a negative weight edge cycle present in the graph. Next, we will see how the Bellman-Ford algorithm works on an undirected graph. Let's learn this through an example. Here, we have a graph of two vertices 0 and 1. So, when we go from undirected edge 0 to 1, the cost will be calculated as 0 plus minus 1, which is equals to minus 1. Now, from edge 1 to 0, the edge will be minus 1 plus minus 1, which is equivalent to minus 2. Now again, if we want to calculate the minimum cost, it will be minus 2 plus minus 1, that is minus 3. And this will be turned as an infinite loop. So, here we come with the 2 points. The Bellman-Ford algorithm works only if all the edges are undirected graph are positive. If an undirected graph has any negative edges, the Bellman-Ford algorithms fail to find a path. For better understanding, let's look at an example for Bellman-Ford algorithm. Assume that we have a graph with 5 vertices. So, we must perform relaxation v minus 1 times, that is 5 minus 1 times, that is 4. Following that is a table in which we will update the minimum cost of the edges of this graph, where the column is for vertices and edges is for the number of edges traversed. Next, we have a list of edges that are 1 to 2, 1 to 3, 2 to 4, 3 to 2, 3 to 4, 3 to 5, and finally 4 to 5. From 1 to 2 edge, the cost will be 0 plus 5, which is equal to 5, which is less than infinity. So that we will replace it with 5. From 1 to 3 edge, the cost will be 0 plus minus 1, which is also less than infinity. So that will be replaced by minus 1. Now from 2 to 4 edge, we have the weight as minus 3. So the cost will be 5 plus minus 3, which is equals to 2. And 2 is less than infinity. So we will replace it with 2. From 3 to 2, we have the weight of minus 2. So the cost will be minus 1 plus minus 2, which is calculated as minus 3. And minus 3 is less than 5. So we will replace with minus 3. Now, from 3 to 4, we have weight as 6. So the cost will be minus 1 plus 6, which will be calculated as 5. But 5 is greater than 2, so we will not replace it. Now we have an edge of 3 to 5, where the weight is 3 and the cost is calculated as minus 1 plus 3, which is 2. And 2 is less than infinity. Finally, we have an edge of 4 to 5, where the weight is 2 and the cost is calculated as 2 plus 2, which is 4. But 4 is greater than 2, so we are not going to replace it. So in the table of the first relaxation, we will now update all the vertices with minimum cost. Now let us move into second relaxation. From 1 to 2 edge, the cost is 0 plus 5, which is equals to 5, greater than minus 3. So we will not replace it. From 1 to 3 edge, the cost is 0 plus minus 1, which is equals to minus 1. But we already have minus 1 as vertex number 3. So we will not update it. Now we weigh minus 3 from the 2 to 4 edge. So the cost is minus 3 plus minus 3, which is equals to minus 6. And minus 6 is less than 2. So we will replace it by minus 6. From 3 to 2, we have the weight of minus 2. So the cost will be minus 1 plus minus 2, which is equals to minus 3. And minus 3 is already there. So we won't update it. Now that we weigh 6 from 3 to 4, the cost will be minus 1 plus 6, which is calculated as 5. But 5 is greater than minus 6, so we will not be replacing it. Now we have 3 to 5 edge, where the weight is 3 and the cost is calculated as minus 1 plus 3, which is equals to 2. And 2 is already there, so we won't update it. Finally, we have a 4 to 5 edge, where the weight is 2 and the cost is calculated as minus 6 plus 2, which is equals to minus 4, and minus 4 is less than 2. So we will replace -4 by 2. So in the table of second relaxation, we will update all the vertices with minimum cost. Now let us move to third relaxation stage. From edge 1 to 2, the cost is 0 plus 5, which equals 5, which is greater than -3, so we will not replace it. From the edge 1 to 3, the weight is -1 and the cost is estimated as 0 plus -1, which equals -1, but we already have -1 as vertex number 3, so we will not update it. Now we have weight -3 from the edge 2 to 4, so the cost is -3 plus -3, which equals to -6, and -6 is already there, so we will not update it. From 3 to 2, we have the weight as -2, so the cost will be -1 plus -2, which equals to -3, and -3 is already there, so we won't update it. Now that we weigh 6 from 3 to 4 edge, the cost will be -1 plus 6, which is calculated as 5. But the value of 5 is greater than -6, so we will not replace it. Now we have the edge 3 to 5 with the weight as 3, and the cost is calculated as -1 plus 3, which is equals to 2, and 2 is already there, so we won't update it. Finally, we have a 4 to 5 edge where the weight is 2 and the cost is calculated as -6 plus 2, and it is -4, and -4 is already there, so we will not do anything. So in the table of third relaxation, we will now update all the vertices with minimum cost. As we can see, we got the exact minimum cost for the third relaxation as we did for the second, which means we will get the actual minimum cost for the fourth time of relaxation. And now we have calculated the minimum cost of all the edges. Following that, we will examine the complexity of Bellman-Ford's algorithm. The Bellman-Ford algorithm finds the shortest path in a weighted digraph from one source vertex to all the vertices. Bellman-Ford is more straightforward than the Dijkstra's algorithm used to find the shortest path between two nodes in a graph and works well in distributed systems. However, the time complexity of Bellman-Ford algorithm is O of V into E, which is greater than that of the Dijkstra's algorithm, because we are relaxing the edges E number by V minus 1 times, where V is the number of vertices. Now, these were the complexities of Bellman-Ford algorithm. Now let us get into practical mode, where we will be executing an example based on Bellman-Ford algorithm. Now, on my screen, you can see an example based on Bellman-Ford algorithm. First, we finished all the necessary header files: standard input-output, standard library, string, and all the console input-output libraries. Then, using the struct keyword, we created an edge. This structure is equivalent to an edge. There are two endpoints to an edge because these are directed graphs. They include the SRC as the source and DEST as destination and some WT as weight, where three components of the structure are as follows. Next, we use the struct keyword to create a graph with two variables, V and E, where V is the number of vertices and E is the number of edges. We also made an edge, and this structure contains another structure edge which we had previously created. Now we have created a function called designGraph which contains V and E. Using the malloc function, we created a graph in this function. We assign V and E values to the structure elements obtained from the user in this graph. Then we make an edge and return the graph. Now we have created a solution which is a function, and this function prints the final solution too. We print the distance from source vertex. For this, we make a loop from 0 to variable n and print the distance. Then we created the Bellman-Ford algorithm function with graph and source variables as parameters, and we assign the vertices and edges to the graph again. Finally, we make an array called saveDistance with size as a vertex. After that, we declare two counter variables I and j. After that, we run a loop from 0 to the number of vertices, and in this loop, we set all distances to infinity except the source, which is set to 0. Now, we run a loop from 1 to v minus 1 times followed by another loop for the edges, and we've declared three variables: u, where we assign the graph source, v, where we assign the graph's destination, and wt, where we assign the graph's weight. Now we have a condition that if the distance of the source node and the weight of the uv edge is less than the distance of the destination node, we update the destination node to be the distance the source node plus the weight of the uv edge. Now we run a loop from 0 to the graph's edge uv and assign all source, destination and weight of the graph, and we have the condition if the distance of vertex plus the edge of uv is less than the distance of destination vertex, then we print a graph obtaining a negative edge cycle and call the solution function and return it. Finally, we have the main function in which we have defined three variables as v, e and s, where v is the number of vertices, e is the number of edges, and s is the source vertex. And we ask the user to print the number of vertices, edges and source vertex, after which we call the design graph function, which prints the source, destination and weight respectively. And finally, we call the Bellman-Ford Algorithm function to implement the Bellman-Ford algorithm. Now I hope I made myself clear with the code. Let's try to run this code quickly and see the output. So to run this code, we might want to press on the execute button. Now let's press the compile and run option. Now you can see that the code got successfully executed and now it is asking for input. Now we will consider the same example that we have seen in the PPT, which is this particular example with 5 vertices and 7 edges and all the weights which are present in this particular image. Now let's get back to the output window and try to provide the inputs. So enter the number of vertices in graph. So we have 5 vertices in this particular graph. As you can see, we have 5 vertices, and enter the number of edges in the graph. So let's count the edges. So 1, 2, 3, 4, 5, 6 and 7. So we have 7 edges in the graph. Now enter the source vertex number. So the source vertex number is 1. So let us provide 1. Now enter the edge 1 properties. So we have to enter the source of the edge 1, its destination and its weight respectively. So here we have the first edge, that is 1 to 2. So the source is 1 and the destination is 2 and the weight is 5. So we have to enter 1, 2 and 5 and so on. So the source is 1, destination is 2 and weight is 5. Now it will ask for the next edge, that is edge 2. Let us finish all the edges from vertex 1. So again we will provide the source as 1 and destination as 3. So the weight is -1. Now enter the edge 3 properties. Now let us go to the vertex 2. So from vertex 2 we have just one edge which is going towards 4. Let us enter the data. Source is 2. Destination is 4 and weight is -3. So let us go to the next vertex, that is 3. So from 3 we have 3 edges. So let us enter the data 3 and the first destination is 2 with weight -2. Now the source will be 3 again. This time it is going towards 4 with weight 6. Another last edge, that is from source 3 to destination 5 with weight 3. Now the 7th edge, that is 4 to 5. So the source is 4, destination is 5 and the weight is 2. So let's enter and we will have our answer. So the vertex distance from the source vertex is, here you can see the answers. So from 1 we have 0 and from 2 we have -3, that is here, and from 3 we have -1, which is over here, and from 4 we have -6, which is over here. And this is how you get the result for Bellman-Ford's algorithm, and this is how you implement it.
The Tower of Hanoi is a mathematical puzzle made up of 3 towers and multiple rings arranged in ascending order of their diameters. The number of rods or tower is fixed, whereas the number of rings can be changed by the player. The setup of this game looks something like this. There are three towers in this diagram, and one of the tower is decked with several number of discs or rings, such that the largest disc is at the bottom and the smallest disc is at the top. A player's goal is to move these discs one at a time to a particular destination tower in the same specific configuration at the start. That means the order of disks should not be changed after being transferred to the destination tower. Before you get ahead of yourself and deem this problem to be trivial, there is one crucial aspect to consider. In this problem, you are not allowed to transfer a larger disk on the top of a smaller disk at any stage. This rule makes solving this problem substantially difficult. However, this problem can be solved using the auxiliary tower or helper tower. By altering the position of disk using three towers, we can take all the disks present at source tower to the destination tower. This is quite confusing, right? So, to make this understandable to all of you, let me give you a rough example. In this Tower of Hanoi problem, we have three rings at the source tower. Now, to attain the same sequence at the destination tower, we'll move the top two rings to the helper tower. After that, we can move a ring with highest diameter to the destination tower. Now, if we just move the two rings present at the helper tower to the destination tower, we'll solve our problem. But let me tell you guys that this explanation was just to make you visualize this problem more straightforward manner. In reality, this problem becomes more complex when the rules for the movement of rings are applied. So moving forward, let's look at those rules for ring movement in the Tower of Hanoi problem. The first rule that we have is at any instance, only one disk can be moved from the tower. That means we cannot move more than one disk at a time. The next rule on our list conveys that a disk can only be moved if it is the uppermost disk of the stack. The last and essential rule is no disk should be placed on the top of another disk that is smaller in size. So let's look at another Tower of Hanoi problem to build solution using these set of rules. In this problem, we have four disks to increase our problem's complexity, whereas the number of towers remain the same. In order to formulate the solution, we are allowed to move these rings into different towers. So the first move we are supposed to do is moving the orange disk to the helper tower. Next, we can move green disk to the destination tower, and after that, we can move the orange disk to the destination tower. We'll place this orange disk over the green disk. Now, our helper tower is empty. So let's take out our yellow ring from the source tower to the helper tower. Now, we'll move the orange ring to the source tower. Further, we'll move green ring to the helper tower. This movement will make our destination tower empty so that we can bring this larger disk to it. Next, we'll move orange ring to the helper tower. This move will make room for the transfer of largest disk to the destination tower. Now, we have brought our largest disk to the destination tower. However, we still need to bring three more disks to our destination tower in order to solve this TOH problem. And to do that, here we'll move orange ring to the destination tower and the green ring to the source tower. After that, we'll move orange ring to the source tower in order to bring the second largest ring to our destination tower. Here, we have successfully placed two rings at the destination tower. Now, we only left with arrangement of two more rings. To attain that, here we'll move orange ring to the helper tower and green ring to the destination tower. Finally, we'll move orange ring to the destination tower. And this is how we'll land at accurate solution to our Tower of Hanoi problem. If you observe this process, you'll get that the process of ring movement is of recursive nature, and we can develop a solution to this problem using recursive programming paradigm. So moving ahead, we'll develop a program to implement a solution to this Tower of Hanoi problem. The language that we are going to use for this implementation is C programming language. So without wasting any time, let's move to the code editor. Here, to begin with our Tower of Hanoi implementation, let's first create an utility function named TOH. So we'll do that, void TOH, and inside this function we'll pass few arguments. The first argument we'll pass to this function will be the number of rings in our TOH problem. So let's call that variable n, and the subsequent arguments will be the source tower, destination tower, and helper tower. All these three arguments will be of character data type, as we want to pass the names of towers here. So we'll create char source, next char destination, and char helper tower. Next, now inside this function body, we'll make recursive call to the same function in order to move the disk. Inside this recursive call, we'll tell our IDE to move n-1 disk from source tower to the helper tower. And to do that, the statement that we'll write is TOH move n-1 disk, that is this n. Next will be the source, then helper underscore t, which will act as destination here, and destination tower will act as an helper tower. So basically this call is nothing but these arguments over here. This recursive call will allow n-1 rings to move from source tower to the helper tower by taking the help of destination tower. So by using this statement, we have moved n-1 rings from source to the helper tower. Next, what we'll do is we want to print all these movements covered by this function. Hence, let's create a format for printing the disk movement using printf function. The format that we'll use is printf, add /n, next move disk modulus d from tower modulus c to tower modulus c. And after this, by taking comma, we'll pass arguments. The first will be modulus d, that is number of tower. Next will be the source, and after that it will be destination. So by moving n-1 disk to the helper tower, we have made space for moving the largest disk to the destination tower. And next, we'll have to move these n-1 rings to the destination tower from the helper tower by using the source node. So for that, we'll write another recursive call, TOH n-1 comma helper underscore t will act as source now, and destination will act as destination, whereas source will act as helper tower. Now, what will be the base case for this recursive function? Well, it's pretty easy. The recursive call we are making is actually decreasing the disk number, that is n-1, and thus after few iterations the value of n will become 0. And when it reaches 0, we want to stop our recursion. So our base condition will be if n becomes equal to 0, we will return the control to the next function. So with this, we have successfully created our Tower of Hanoi function. Next, we'll move to our driver method, that is main method, in order to contemplate the TOH function. So what we'll do is we'll pass arguments to TOH function. The number of rings that we are going to use for this problem will be 4. And let's call our towers as A, then B, and C and return 0. Now let's check if our code works fine or not. Okay, so we are getting one error over here, semicolon missing. Okay, so let's add that semicolon and rerun our code. Okay, so we have received output here. The output is 15 steps that we have discussed earlier for the 4 rings TOH problem. And that output is what we have received here. That means our program works accurately. You can verify this output by matching these movements with the previous solution that we have discussed earlier. The only thing to note here is that the tower B is acting as destination, tower A is acting as source, and tower C is acting as helper tower. I hope you guys are clear with Tower of Hanoi implementation now. This is all about Tower of Hanoi implementation using C programming language.
With that, we have come to an end of this session on dynamic programming. I hope the session was informative and interesting. If you have any queries regarding any of the topics covered in this session, or if you need the codes executed in this session, then please feel free to let us know in the comment section below, and our team of experts will be happy to resolve all your queries at the earliest. Until next time, thank you, stay safe, and keep learning.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.